You have now seen the A-star algorithm for heuristic search, and you should understand how it works. A-star is a pretty good algorithm. It always finds optimal solutions, and it is optimally efficient. So you may wonder, why would we ever need another search algorithm? Well, there are a few more problems, and I will go into those next. Some of these problems are related to the fact that we're usually searching a graph, not a tree. So we will look at A-star as a graph search algorithm next. And here is the pseudocode for the A-star tree and graph search algorithms. The basic version of this algorithm is the tree search algorithm, and there is an extension that I've also included on this slide, which consists of 3 additional lines of code that performs the graph search. And the 3 additional lines of code are these 3 lines here shown in gray. But let's have a look at the tree search algorithm first. So we define a function A-star tree search that takes 2 parameters. The first is our search problem, and the second is the heuristic that we're using. This may or may not be an admissible heuristic. The first thing we do then is initialize our set of fringe nodes, and we initialize the fringe from our initial state that was given in the problem. And what we do is we put this initial state into a queue, into a priority queue that sorts the node by their f value. That means we always have quick access to the node in that queue that has the lowest f value, and that is how we initialize our fringe. Then we go through the loop that does the node expansion and generates the search tree. The first thing we do is we test whether the fringe is empty. That would mean there would be no more nodes to explore, and that means we can return failure, because it means we have generated the whole search tree and haven't come across a solution node, so there is no solution node, so we can return with failure. But if there are nodes on the fringe, then we have to select one of these nodes for expansion. Note that the select function here does not take a second argument as it did earlier. Because our strategy here is fixed, we select the node with the lowest f value. Having said that, I should point out that this selection is not quite deterministic, as there may be many nodes with the same f value that are currently on the fringe. So our node is only one of the nodes with the lowest f value. And what we do next is we perform our goal test, the goal test on the state contained in that node, and if this goal test succeeds, that means we have found a solution, and then we can simply return the path to this node in the search tree. If our chosen node is not a goal node, then we have to add its successors to the fringe. And I've shown this here as a loop because we add each successor in turn, and we use the function expand to generate all the successors of the selected node. And our loop variable successor here is the next successor in that loop. And then for the tree search version of this algorithm, we simply have to add that new successor to the fringe. So we extend our current fringe with the new successor, and the place where we queue this new successor in our priority queue is, of course, the f value of that node. And for those of you who've been wondering where we use the parameter h, that is the second parameter to this function, remember that f is defined as g plus h. So that's where we use our heuristic function. And that is all the pseudocode we need for the tree search version of this algorithm. But the graph search version isn't much more complicated. What we need to do in addition is, first, we need to initialize the set of all nodes that we have seen so far. And one way to do this is to initialize this as a hash table of nodes. And initially, this will contain only the initial state that we can take from the fringe or from the problem. Then the algorithm proceeds as before, going through the loop, trying to take a node off the fringe if there is one, performing the goal test on that node. If it's a goal node, then we found a solution. And if not, we go to the loop where we expand the current node and generate its successors. And that's where the algorithm for graph search differs. Namely, for each successor that we are generating, we have to test whether this is a node that we've already seen. And if we have already seen that node, then we don't need to add it to our fringe. If we haven't seen the node, then we continue as before. We add it to the fringe as our new successor at its current f value. And we also have to add it to the set of all the nodes we have seen before, so that we don't explore this node again. So this is a working version of the graph search algorithm. However, there is one problem with it. If the given heuristic is admissible, the graph search version, as shown here, no longer guarantees an optimal solution. And the reason for this occurs here. Namely, if we generate the successors of a node, we may generate a new node that we have seen before, but the second time we generate the node, we actually discover a shorter path than the first time we generated it. So what we really want to do here is keep the node that has the shorter path, and it doesn't matter whether we discovered that first or later. So what we could do is simply add a piece of code here that tests whether our new path is shorter than the old path. But for many problems, the heuristic that we'll be using is not admissible, and then A* doesn't guarantee us an optimal path anyway, so we don't have to worry about this shortcut question necessarily. And here is the first problem with A* as it stands, and that is it still uses exponential space unless the heuristic is perfect. In fact, in the worst case, the time and space complexity of A* are both in O of b to the L, where b is the branching factor, so that's the number of successors we have per node on average, and L is the length of the path we're looking for. B to the L is exponential, which means we have exponential time and space complexity. And in reality, we will see that this is true. Most of the time, the fringe grows exponentially. Now let's look at this. What does this really mean? So exponential time complexity. That means when the problem grows by one step, the size of the problem, the time it takes to solve this problem, doubles. Or in general, it grows by a factor of b. This may or may not be acceptable depending on how much time you actually have. When it grows into the region of years and centuries, this will no longer be acceptable, of course. But quite often we have another hour we can give our algorithm. But what about exponential space complexity? Well, what this means is that A* will eventually exhaust the computer's memory. So first it will eat up all the RAM, then it'll eat up all the virtual memory, and eventually it'll just have no more memory left. And what happens then? Well, A* simply fails. The algorithm terminates because it's out of memory, and we don't even know whether there is a solution or not. As an example, the 8 puzzle will still fit into memory, but the bigger version on a 4x4 grid, the 15 puzzle, usually does not fit into memory.